Welcome to this topic on the internal rate of return. This is one of the techniques that's used in investment appraisal. This is a discounting technique very similar to the net present value, which is dealt with in a separate video. The internal rate of return is slightly more complex, and it does involve a little mathematics, as we'll see later on, but nothing to worry about really. So the present value formula, which is related to the internal rate of return, has the same format, was that. And just to recap for a second, if I put the cursor on the square, here we have a stream of income over a period of time, the life of the asset, the life of the investment. And here's the rate of interest, and we discount the stream into the future, the stream of returns, by the rate of interest to give us the present value of that sum of money. In this equation, of course, we've got one variable, we've got one unknown, which is the present value, and everything else we're given that the stream of income is into the future and the rate of interest. Please note, of course, that the stream of income going into the future is just an estimate. We can't know the future, we can't know it with certainty, and therefore we use estimates of the likely returns in the future. The internal rate of return finds the value of the discount rate that makes the net present value equal to 0. So it's the same formula really, but it's just solving something differently. It's saying if we have the stream of returns in the future from the investment, whatever they are, year 1, year 2, year 3, and so on, and if we know what the cost of the investment is, which we should do because it's happening now, then we would solve for this one here, the internal rate of return. In other words, we're looking for an internal rate of return that will balance the future stream of income with the cost of the investment. Let's look at the formula again. There's the formula, and we know what the present value is. It's it's the cost of the investment, which is happening now. So we know that with certainty. What we don't know, of course, is what the future stream of income is. So we only have estimates of that, and we have no idea what the balancing rate of internal rate of return is. This figure here balances the two sides of this equation, makes both sides equal. That's the formula we actually use. The cost of the investment, the future stream of returns, and we're trying to find I, which is the internal rate of return. So this is the formula we're going to play with, this one here. This is the one which concerns us. And we'll see that the problem arises here for time periods greater than 2. Because if you notice here, we've got to the power of n. Well, once we get into 2, 3, 4 time periods, n to the power of 4, we can't calculate it. It's very, very difficult. And we'll be forced into trial and error and different techniques. However, if we can find it, the rule is simple. If the internal rate of return, the return on the asset, exceeds the rate of interest, what we paid to borrow to fund the investment, then the project should be carried out. If you can get a rate of return on the investment of 10% and it costs you 9% to borrow the money, you're making 1% profit. Perhaps it's worth doing. Conversely, if the internal rate of return is less than the rate of interest, then the project should be rejected. Let's have an example. Let's say there's an investment opportunity which costs £100,000 and it yields a one-off return of £108,000 in 1 year's time. Now, if the rate of interest is 9%, should the investment be undertaken? Well, let's put in our formula, which is there. And now let's plug in the information into the formula. Well, we know the cost of the project, it's 100,000, so C is equal to 100,000. The stream of income in the future, well, there's only one of them, which is 108,000 in a year's time. So in this case, the cursor back here, in this case n, it's only one time period, so n is equal to 1. And any number to the power of 1 is just the number itself. So 10 to the power of 1 is 10. 2 to the power of 1 is 2. 1 plus I to the power of 1 is 1 plus I. So the n drops out, not needed. If we cross multiply here, just cross multiply, we get that. And just dividing across, or just moving, getting rid of the brackets, I should say, gives us this, and subtracting 100,000 from 108,000 gives us 8,000 on the right hand side. So 100,000 I equals 8,000, divide by the 100,000, and we get 8%. So that's the upshot of this calculation, that the machine or the investment gives us 8% return, but we pay 9% to borrow the money to fund it. So don't do it. This project fails, is not undertaken. Let's have a different example. A project, say, again 100,000, and has two returns only, one next year and one the following year. These returns are 60,000 and 65,000 pounds respectively, and the rate of interest in the bank, let's say, is 8.5%. So should we undertake the project? Back to the formula, which is there. Here in this case I've extended the formula, so we have the first time period, the second time period, plus 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 plus, and the nth time period, some time period in the future. In this case we've only got two time periods in our question, so we'll be cutting it off at A2 on this one here. So the formula really looks like the one we've got there. Now let's insert the information into the question. Right, so that's inserting the information. We've got 100,000 is equal to, in the first year we get 60,000 back, in the second year we get 65,000, but we have got this little square term here, don't forget. To solve this, you really need to be familiar with quadratic equations. So think back to your school days. It's not difficult, but we just have to confront it. So multiply each of the terms here by 1 plus I squared. So we get that times 1 plus I squared. We get equals 60,000 times 1 plus I, because this one here would cancel out part of that, and that's squared. So our equation would look like this. We've multiplied up, equals that plus that. Now we need to tidy this one up and solve it. Find a value that balances the two sides. So we need the rate of interest here, which equates the two sides. Balances the right hand side over here with the left hand side C. It looks a bit messy and it looks a bit daunting, but the logic is quite straightforward. We started with this one here, just note this one. and now we go to here. So we just expand the first term. So when you 1 plus I squared is equal to 1 plus 2I plus I squared. Get rid of the bracket and we get that. Multiply everything inside the bracket by 100,000 and you get this, which is equal to, just tidying this lot up here, 60 plus 65,000 is 125,000 plus this one. And collecting everything onto the left hand side gives us the standard form of a quadratic equation. This one is not easy to solve, so we divide out by 1,000 just to make it a bit easier to do the arithmetic, to do the calculations. And we would use the quadratic formula, which you've bumped into back at school, chances are, which is equal to that. Now, insert the figures in here. This is a standard formula, so we can easily substitute the figures in there, and we would get this. Actually, it's the same as this one. I just duplicated those. Sorry about that. Anyway, we get this one, which gives us this one here. And we ignore the negative return, so we just work out here, and we get it down to 16.03%. Now, the company can borrow the funds for 8.5, that's what the question said, and we get a return of 16.03%. So therefore it's worthwhile to borrow the money and make this investment. The internal rate of return, 16.03%, is greater than the rate of interest, 8.5%. So it's worthwhile. If there are several time periods, then it may be impossible to solve the equation systematically. In this case, we normally use a trial and error method. One way to do it, I suppose, is to use a spreadsheet. Just model the equation on a spreadsheet and iterate, try different rates of internal rates of return, different figures, to try and balance the two sides. That's a possibility. Let's look at the trial and error method again. It involves guessing a rate of interest and calculating the equation. For example, assume that the cost of an investment project is 5,000 and the returns are spread over 3 years, say 3,000, 1,500 and 900. Now the problem is that it's over 3 years and we have this cubic term here, 3. This cubic term makes it difficult. We can't use our quadratic formula. The equation is altered by this cubic term. So we try to find different values of I, this one here, different values of the internal rate of return, which balances this. And then we compare this with the rate of interest to see if the project is worthwhile. We could use discount tables. These are available. You get them online and you get them in good bookstores and sometimes at the back of financial books, and you fall across them. Discount tables could be used as follows. Say we have the problem above. Say we set up the problem as this. The project cost us 5,000 and we're going to get 3,000 in the first year and 1,500 in the second and 900 in the third. Now we try to find D1, D2, D3, and these are figures in the discount table. Now let's try 10%, just for no apparent reason. Just try 10%. Well, from the tables, there's a 10% set of figures from the tables. Now you'd have to find these tables, as I said, at the back of a finance book or in the local library, or I wouldn't suggest you buy them, but they are available. And when you look it up in the tables, you'll find these figures here. So what you would do then is you would say, okay, therefore 5,000 is equal to 3,000 times 0.91 plus 1,500 times 0.83 plus 900 times 0.75. When you add up the right hand side, it comes to 4,650. That's not 5,000. So it's wrong. So you need to try a different figure. Figure on the right hand side is too small. So instead of 10%, try 9%. Or try a different figure until finally you get to a balance, or almost a balance, and that becomes the internal rate of return. As I said, it's slightly more complex than the net present value, and certainly more complex than the non-discounting techniques such as the payback method, which is in a separate video. But it is useful because we often think, what is the return on an asset? And then we compare the return on the asset to what we would have to borrow the money to purchase the asset. So it is popular in that sense. It is spoken about, and it's one we should be familiar with. But essentially it's just finding the return on a specific asset and comparing it to the market rate of interest. So that's our introduction to the internal rate of return discounting technique for investment appraisal. Thank you for watching.